Hello everybody, I am Susha Lekshmi. Here I am going to give you a presentation on my research work entitled as Evaluation of TDR and Capacitance Techniques for Soil Moisture Measurement. This research work was carried out in the Department of Civil and Environmental Engineering, University of Strathclyde, Glasgow during 29 January to 2 April 2015. Here, I would like to thank my supervisors for this research work, Professor D.N. Singh, IIT Bombay, India, and Professor Alessandro Tarantino, University of Strathclyde, Scotland, for selecting and giving me an opportunity to carry out this research work as part of great project. Geotechnical and geological responses to climate change, exchanging approaches and technologies on a worldwide scale. Great projects brings an opportunity to exchange knowledge among research institutions in the world in the area of geotechnical engineering inclined towards climate change. Here, I also would like to acknowledge the funding received from European Commission via the Marie Curie IRSES Great Project. Here, I am going to give you a brief introduction of the significance of this research work. What is soil moisture content? It is available water present in the soil mass. It can be in different forms such as free water, capillary water and hygroscopic water. Soil moisture content is an inevitable part of the three-phase system of the soil mass and has paramount importance in dictating engineering, agronomy, geological, ecological, biological and hydrological characteristics of the soil mass. Hence, its significance falls in various fields of engineering. When we talk about agricultural engineering, especially for proper plant growth and crop yield, monitoring of optimum moisture content is indeed required. In the case of geotechnical engineering, mechanical properties of the soil mass such as consistency, compatibility, cracking, swelling, shrinkage and density are dependent on the soil moisture content. In the case of environmental engineering, it has tremendous influence on contaminant transport. Moreover, space-time evolution of the soil moisture content is controlled by topography, landscape position, slope, vegetation, soil structure, texture and human-made structures. Considering the applicability of soil moisture content in different fields of engineering, I would like to coin soil moisture content as an interdisciplinary parameter. Basically, soil moisture content can be measured on two bases, gravimetric basis and volumetric basis. Gravimetric moisture content is the ratio of mass of water present in the soil to the total mass of the soil solids, whereas volumetric moisture content is the volume of water present in the soil to the total volume of the soil mass. Both these moisture content can be correlated by using dry density, D of the soil mass as shown here. I had carried out an exhaustive and comprehensive critical literature survey on the state-of-the-art technologies for measuring the soil moisture content, and the review is published on an International Journal of Measurement in 2014. From the study, I could synthesize that dielectric techniques such as time domain reflectometry TDR and capacitance techniques CT have gained much more popularity mainly due to the dependence of the dielectric constant or apparent permittivity on the soil moisture content. For dry soils, dielectric constant varies between 2 to 8 and for water it would be 81. Dielectric techniques also gained popularity due to revolutionary development in the field of electronics and data communication system in the recent past, which facilitated them as instantaneous and non-invasive measurement techniques in the porous materials. With this in view, efforts were made to compare the relative performance of time domain reflectometry and capacitance techniques on the soils of entirely different characteristics and various compaction states. For carrying out the experiments, 5 soils of entirely different characteristics collected from various parts of India and 2 standard fine grade sands were selected. By employing the standard procedures, soils were characterized based on their physical, chemical, and mineralogical characteristics, which ensured that soils are having entirely different characteristics. The dielectric techniques employed were TDR Campbell Scientific CS640 probe and decagon device 5TE capacitance probe as shown here. The soil was mixed with deionized water and left for maturation for 24 hours, which ensures uniform moisture level of the entire soil mass. Later, it was compacted to different compaction states in a standard Proctor mold as per the ASTM procedure. Simultaneously, 3 specimens of matured soils were used for determining gravitational moisture content by employing oven drying method. The volumetric moisture content, electrical conductivity, dielectric constant of the compacted soil mass were determined by employing these 2 techniques in a sequential manner. TDR setup basically provided the TDR waveforms of the soil sample, whereas capacitance probe directly gave the values of volumetric moisture content, dielectric constant, and electrical conductivity of the soil samples. Hence, a detailed studies of TDR waveforms were carried out. Here, you can see the TDR waveform depicts a relationship between the reflection coefficient ρ and the time of reflection t. Reflection coefficient describes how much of an electromagnetic wave is reflected by an impedance discontinuity in the transmission media, which is quantified by the ratio of amplitude of the reflected wave and to the incident wave. The most established methodology proposed by Top, Himover, and Boughton were employed for determining dielectric constant of the soil mass as shown here. It basically deals with the determination of travel time, which is the difference between the time of reflection at the head of the probe, which is designated as T suffix head, and time of reflection at the end of the probe, which is designated as T suffix end. Here you can see that the time at which the reflection occurs from the head of the probe would be constant, but the time at which the reflection occurs at the end of the probe varies for different media in which TDR probe is inserted. You can see T end is higher for water. This indicates that an increase in moisture content of a medium results in an increased Tn and hence increased dielectric constant, which results in increased volumetric moisture content. On the contrary, the presence of salinity in the medium makes it more conducting and hence Tn decreases. Increase in conductivity of the medium is also responsible for its short circuiting at the surface of the insertion and hence Tn cannot be determined. Electrical conductivity can be calculated from ρ max, which is a reflection occurring at infinite time, by employing an equation given by Top in 1988. For further understanding of the effect of conductivity, standard fine-grained sands were saturated with the different molar concentration of the per solution of sodium chloride. And the results of sand H7 is shown here. It can be noticed that as sodium chloride concentration increases, the dielectric constant decreases. This can be attributed to the fact that presence of salinity in the medium increases its conductivity, which results in a decreased T head and hence decreased dielectric constant. Volumetric moisture content of TDR, theta TDR, was calculated by using a well-known equation known as Dobbs equation, which is a polynomial equation relates dielectric constant and volumetric moisture content. Volumetric moisture content from capacitance probe theta CT was directly obtained from the instrument. However, it is mentioned in the manual of decagon device of 5T capacitance probe that this capacitance probe also employs Dobbs equation to derive volumetric moisture content from dielectric constant. Here you can see that moisture content obtained from both techniques for a given sample is not unique. Volumetric moisture content obtained from the capacitance probe is about 50% of the value obtained from the TDR probe. Moreover, electrical conductivity obtained from capacitance probe for these soil samples is 25% higher than that obtained from TDR. For standardization of these observations, all these parameters were compared against the calculated volumetric moisture content theta C, which is obtained from gravitational moisture content and dry density of the soil mass. An increasing trend between dielectric constant and electrical conductivity indicate that starting from dry of compacted soil sample which contains air in the voids get replaced by the water, result in an increased theta C. Here I am going to explain the philosophy of comparison of the dielectric constants obtained from different methods for the soils. As TDR and capacitance probes employ Dobbs equation to correlate dielectric constant and volumetric moisture content, dielectric constants obtained from TDR and capacitance probes of the soil samples were also compared with those obtained from Dobbs equation. From this figure, it can be noted that a linear relationship exists between dielectric constants obtained from top and TDR and capacitance probe and top, though it appears to be an overprediction of TDR values and underprediction of capacitance probe values with respect to Ka top. As top equation does not incorporate soil specific parameters, dielectric constant obtained from these techniques were also compared with the TP mixing model, which incorporates soil specific parameters such as porosity, fraction of minerals, dielectric constant of minerals, and dielectric constant of pore fluids. However, the quantification of mineral fraction and dielectric constant of these minerals are an arduous task. Hence, a relationship is derived by relating dielectric constant obtained from all these methods. Interestingly, this hypothesis or relationship would be useful for calculating volumetric soil moisture content without resorting any techniques. These are the two references cited here. Thank you.